Hello everyone, welcome to today's lecture. In this session, we will discuss an important topic in maintenance equipment failure patterns and their analysis, and the concept of failure mode effects and criticality analysis or FMECA. Understanding how equipment fails help us plan maintenance intelligently, improve reliability, and prevent costly breakdowns. So, let's begin by exploring the purpose of studying equipment failure patterns. The main purpose of studying equipment failure pattern is to help us determine maintenance requirements and timing. By understanding these patterns, engineers can predict how and when equipment is likely to fail. This knowledge allows us to plan preventive and predictive maintenance, minimizing downtime and maximizing efficiency. Now, equipment failures don't occur at random. They tend to follow certain identifiable patterns over their lifespan. There are six major failure patterns labeled A to F, and each one describes a different type of failure behavior. Let's go through each one of them one by one. Pattern A is called the bathtub curve. It shows a high failure rate when the equipment is new and again a high failure rate at the end of its life. In between these two stages, there is a period of low random failures. This pattern represents about 4% of all equipment failures. Early failures are usually due to manufacturing or assembly issues, while end of life failure occurs due to wear and deterioration. Pattern B is known as the wear out curve. This curve shows low random failures in the early stage, followed by a sharp increase in the failures as the equipment approaches the end of its life. It accounts for about 2% of failures. Wear out failures are typically caused by aging, corrosion, or erosion, common in parts like bearing, seals, and filters. Pattern C is called the fatigue curve. It's characterized by a gradual increase in failure rate over time. This happens due to fatigue, stress, or material degradation. It accounts for about 5% of total failures. An example would be a metal shaft or a structural part that weakens under repeated load cycles. Pattern D is the initial break-in curve. It, it starts with a very low level of failure but then rises sharply and stabilizes at a constant failure level. This type of this type accounts for about 7% of failures. It represents the early adjustment period when machinery is setting into normal operation. Minor faults may occur before stabilizing. Pattern E is called the random curve. Here failure happens randomly over the life of the equipment. There is no clear pattern related to time or usage. This accounts for about 14% of failures. Random failures often occur due to unpredictable causes like human error, external influences, or random component defects. Pattern F is known as the infant mortality curve, and it's the most common of all. It shows a high initial failure rate when the equipment is new, followed by a steady random failure rate afterward. This pattern represents about 68% of all failures. These failures are mostly caused by manufacturing defects, poor installation, or initial maintenance errors. Once these early issues are resolved, the equipment tends to perform reliably. Now let's analyze what these patterns tell us. Pattern A, B, and C shows failure rates increase as the equipment ages, either due to wear, erosion, or corrosion. These are typically related to simple mechanical components. Pattern D, E, and F shows the most failure occurs during the initial startup or early life of equipment. These failures often arise from manufacturing defects, maintenance errors, or material flaws. After this early period, the failure rate tends to become random and steady. In both cases, understanding the pattern helps us decide the best maintenance approach. For failures that don't fit these patterns, we rely on conditioning monitoring, observing parameters such as vibration, temperature, and pressure to determine the right time for replacement or overhaul. This approach is called condition based maintenance or predictive maintenance. Next, Let's look at failure mode effects and criticality analysis, or FMECA. It is a systematic method used to reduce failures and release or and increase reliability of machinery systems. It helps identify, evaluate, and prioritize potential failures modes and their effects before they lead to actual problems. Basic concepts of FMECA. In FMECA, every failure is analyzed as a three-part event. First one is cause, the reason behind the failure, such as corrosion, fatigue, or a design flaw. Second, failure mode, the manner in which the failure occurs, for example, cracking, leakage, or overheating. Third is effect, the impact that failure has on safety, the environment, or the operation and business performance. FMECA also evaluates the risk associated with each failure mode. The three main risk factors considered are: first one is probability of failure occurrence. How likely is it that the failure will happen? Severity. How serious are the consequences for the vessel, crew, or operation? And the third one is detection. What is the chance that the failure or its cause will go undetected before it becomes critical? By analyzing these three aspects, engineers can identify which components pose the highest risk and must be prioritized during maintenance. The purpose of FMECA is to help engineers identify critical components and prioritize maintenance tasks based on risk and impact. It enhances safety, reliability, and cost effectiveness of shipboard operations. FMECA also forms the foundation of preventive and predictive maintenance programs, making maintenance more organized and data driven. To summarize this lecture, understanding failure patterns also allows better maintenance planning. The majority of failures occurs in the early life of the equipment, known as infant mortality. Age-related failures are less frequent but predictable. Condition monitoring and FMECA together help engineers adopt a proactive maintenance strategy. The goal is to minimize risk and maximize equipment reliability. Thank you for the attention. In the next class, we will explore maintenance and repair expenditure and spare parts and stores.
In this media, you are going to learn about equipment failure patterns. A study of these patterns helps in deciding the maintenance requirements. Pattern A. It is known as the bathtub curve, and it shows an increased probability of failure at the initial and final stages of the equipment life. Pattern B. It is known as the wear out curve, and such equipment displays low rate of random failures during the initial stage and a sudden increase at the end of its life. Pattern C. It is known as the fatigue curve, and it is a slowly elevating graph that shows increasing level of failures over the course of the life of the equipment. Pattern D. It is called initial break-in curve, which starts with a very low failure rate and is followed by a sudden hike to a steady level. Pattern E. It is named as random pattern, and it denotes sustained level of random failures throughout the equipment life. Pattern F. It is called infant mortality curve, which shows high failure rate at the initial stages and a sudden drop to a low steady level at the later stages. The percentages of random failure for these patterns A, B, C, D, E and F are 4%, 2%, 5%, 7%, 14% and 68% respectively. Analysis of the failure patterns. Patterns A, B, and C indicate that the failure rates increase once the equipment reaches a certain age that is mentioned in time or usage hours. These three failure patterns are usually related to wear, erosion, or corrosion and are often simple components. The other patterns D, E, and F largely indicate that during the initial startup of the equipment, the majority of failures take place. This could be due to maintenance in the initial stages or due to manufacturing or material defects in the components. Once the initial startup period is over, the failure rate is usually random, and these patterns are applicable to a large number of failures. In cases of failures other than the above, the equipment needs to be monitored for its condition, and the findings of such monitoring shall indicate the right time to carry out a replacement or an overhauling exercise. This is known as condition-based maintenance or predictive maintenance. Thus, we have learned about equipment failure patterns. In this media, you are going to learn about FMECA. FMECA or Failure Mode Effects and Criticality Analysis is one of the methods to reduce failures and to increase reliability. A sample FMECA worksheet is as shown. Basic concepts behind FMECA is that the failure is considered as three-part event named as 1. Causes of failure, 2. Failure mode or the means by which failure starts itself, 3. Effect or the impact on humans, environment and business. Concepts of risk analysis. The risk associated with failure of component or the system can be grouped as follows. A. Occurrence. Probabilities of failure occurrence. The occurrence ranking criteria is as shown in the table. B. Severity. The extreme of consequences to the vessel due to that failure. The severity ranking criteria is as shown in the table. C. Detection. The risks that can be formed when the diagnosis of the failure mode and the cause of failure are neglected. The detection ranking criteria is as shown in the table. Also, the risk priority number RPN can be obtained by multiplying the rankings of occurrence, severity and detection. Based on the above explained concepts, the FMECA worksheet will be filled up as shown. Then, for carrying out the criticality analysis, risk priority numbers will be calculated based on the SOD rankings. After the criticality analysis, necessary recommendations will be given for improving the system performance. The proper actions to be taken will also be noted to reduce the probability of failure. Finally, the resultant RPN or risk priority number will be assessed. Thus, You have learned about FMECA,